This conference will now be recorded.
Yeah, very good morning, dear participants of second year ECEA and B section. We are now in the classroom, our next learning session of electromagnetic fields, wherein I think this particular GoToMeet will help us. Okay, this is the actual old version of the GoToMeeting before upgradation. So what is the benefit here is it will not consume a lot of power as you stated a problem, right? So new app only it will do that, and also new GoToMeet app is troublesome for the presenter also. So screening, I mean sharing the screen, sharing the camera, everything got a problem. That's what we faced trouble during last week and yesterday also. So yesterday, fortunately, we had a Google Meet link and we conducted class using that. Today, I made some arrangement with the old GoToMeeting link. Okay, old app actually. So it will not consume much power, much data, as you stated, and also there is no problem for the presenter also. Okay, so that is the actual plan, and I have waited for this particular tool only. Okay. So what we are learning now, where we are actually running in this, we are in the verge of completing the second module of electromagnetic fields. So the left out portions, left out topics are like we have derived now the electric field intensity expression, in turn potential expression for different geometries. So till now we have completed 4 geometries. One is like the line charge. Then we have seen uniformly charged circular disk. In turn, their extensions like infinite plane sheet and 2 infinite uniformly charged sheets. So yesterday we have completed all the 4, and today we will be focusing towards some more topics. Like we will be deriving first the Poissons and Laplace equations, which is very important. Next, we will move on to the electric dipole. So what is the dipole we will see, what is dipole moment we will see. Then we will start deriving the expression of electric field intensity and in turn electric potential as usual for a dipole. For a dipole arrangement, we will do that. Then we will move on to the basics of equipotential surfaces we will see. Then we will move on to the basics or concept of capacitance, because as far as electric field or electrostatic field is concerned, we will be seeing the charges. Okay, so whenever we are speaking about charge, electric charge, the term capacitance will come into picture. Okay, there is no doubt at all in it. And as far as magnetic field, magnetic flux is concerned, automatically our inductance will come into picture. And in second module, we will be focusing towards capacitance, and we will be deriving the expression of capacitance for various geometries. That I will give it as a hint actually how to do that. And derivation of the expression of capacitance, if I am having 2 dielectric media, or if I have got 3 dielectric media, what is the expression for capacitance, that we will see. Along with that, we will derive the energy stored in a capacitor and energy density of electrostatic field also. And tomorrow we will be going into the very important topic of our course, boundary conditions, we call it as. See, this particular boundary conditions is very important as far as our course is concerned, because the same question, boundary conditions derivation or obtain the boundary conditions, it is important, and without this particular question, nobody can set the question paper. Okay, so derive the boundary conditions for electrostatic field means it is from the second module. If the question is for a magnetostatic fields, it becomes the boundary conditions from the third module. Or if it is asked like obtain the boundary conditions for an electromagnetic field, like that, if it is asked, it means it becomes the fourth module, because in the fourth module we are actually going to combine both electrostatic field and magnetostatic field. Electric field and magnetic field combinedly we call it as electromagnetic field, and fourth module, there is one boundary conditions, which we are going to derive the boundary conditions for electromagnetic field, combined electric and magnetic fields. So out of these three questions, definitely one question will come. Okay, from any of the unit, maybe from first unit, I mean second unit, maybe from third unit, or maybe from fourth unit. Definitely one question will come out of this particular boundary conditions. So that much this particular question is important, that we will be covering by tomorrow. And probably we will try to complete the second module by tomorrow, or rare case by Saturday, because next to tomorrow is we have got only on Saturday. So definitely by this Saturday we will close second module, and we will start the third module. Okay, only thing left out will be the problems, tutorial problems as far as the second module is concerned, that we will allocate a separate time. Okay, and we will work out the problems separately. Okay, that is our plan actually. And now with this particular base, I'll start sharing the screen. 1 minute. I'll go to the PPT. 1 minute. Okay. Yeah. Screen share. Yeah, I have got a screen here. Is here. Good. Are you able to see the PPT? Yeah, Marilyn, thank you so much again for your kind response. Rajeshwari, thank you so much. So coming to this particular PPT, as I said, today our focus will be on these titles: Poissons and Laplace's equation. We will go for electric dipole, equipotential surfaces, and some basic concepts of capacitance we will go into. Okay, that is our plan. Good. So agenda for today, it goes like this. Revision of the previous class. What we have discussed yesterday is we have discussed about the derivation of electric field intensity, and in turn electric potential for a uniformly charged circular disk we have seen. Along with that, we have seen two more configurations, like its modifications or extensions, I can say. One, infinitely charged sheet. What is the expression for E, electric field intensity? And also we have seen the expression of electric field intensity for two infinite uniformly charged sheets. So that's what we have seen yesterday. And today our focus is Poissons and Laplace's equations. We will derive first, then we will enter into electric dipole. And then electric dipole, as I said, we will be deriving again the expression of electric field intensity and in turn potential. Then we will see something about equipotential surfaces. Then we will see or start the concept of capacitance. And I will give you the hint how you can calculate the capacitance for different geometries. Then with that we will go to the summary. Okay, that's our agenda for today's class. As far as course outcomes are concerned, we are now in second module. So CO2 is our course outcome. Course outcome 2 is analyze field potentials due to static charges and static electric fields, which is coming under K4 level of Bloom's revised Bloom's taxonomy. So K4 is analyze level. So analyze field potentials due to static charges and static electric fields is the actual course outcome. Okay, now let me go into the derivation. Very simple derivation it is, but it is very, very important also. Derive the expression, or I can say like derive Poissons and Laplace's equations of electrostatic fields. If that is the question, then this becomes the derivation, because that is a separate Poisson's equation derivation for magnetostatic fields, which is in third module. Okay, so this is as far as second module is concerned. So very simple. Here we will be using three basic relations which we have seen already. Okay, very basic relations. Okay, so point is we are going to use Gauss law in point form. We have already derived and we have discussed about Gauss law. Am I right? What is the statement of Gauss law? Can anyone tell? What is the statement? Mathematical statement or grammatical statement? Whichever is convenient to you, you can tell. Can anyone unmute and speak out? Esma, have you got my question? Can anyone state Gauss law? Electric Gauss law,
Dot
we
D
call it.
equal to rho v, sir.
Yeah, Sibikanna, come again.
Del dot D equal to rho v, sir.
Yeah, del dot D equal to rho v is the Gauss law in point form. That is available in the screen itself. Okay, very good, Sibikanna. Aishwarya, can you state Gauss law?
State that the electric flux passing through any closed surface is equal to the total charge enclosed by the surface.
Yeah, very good. The mathematical definition of Gauss law is psi is equal to q. That's all. Very simple. Psi is equal to q. What is that psi notation? It represents. It is nothing but electric flux. Psi is the notation used for electric flux. And electric flux, if it is equal to the total charge enclosed in the surface, it is the Gauss law actually. Okay, and whatever Sibikanna has told, Gauss law in point form, that is what Sibikanna has given. It is del dot D is equal to rho v. Can anyone state what is rho v and what is D is? Yes, shall I get Renuka Devi in mic B section?
Yes, sir.
Yeah, Renuka, good morning.
Good morning, sir.
So Gauss law in point form, del dot D equal to rho v is the Gauss law, right? Can you tell
Yes,
me what is D and what is rho v?
sir, rho v is the volume charge density, sir.
Okay, super. D
And
is
del dot v is the divergence of electric flux.
electric flux
Electric flux
density.
density, sir.
Okay, the other name of electric flux density is? I have got another name also. Electric flux density is also called displacement density. Okay, that also you can remember, no problem. Okay, so in the next step, what? Okay, Renuka Devi, thank you so much. So in the next step, what we are doing is actually, we know already one relationship. 1 minute, I'll take some pin so that it will be easy. See, we know one relationship between D and E. What is that? D is equal to, what is the relation? Epsilon E. Am I right? This is the relationship that is connecting electric flux density with electric field intensity, right? Where D is the electric flux density and E is the electric field intensity, and epsilon is the permittivity of the medium. So once I know this particular expression or relationship, means in the place of D, what I am going to do is I am going to put epsilon E here. Is this correct? No? So I'm going to put epsilon E. Epsilon being constant, I will be taking this epsilon to the, outside the differential. So epsilon is going to come outside. So it becomes epsilon into del dot E is equal to rho v. Okay. Also, we know another relationship. Another relationship. What is that relationship? Is yeah, 1 minute. I take this color quickly. Okay. Yeah, the relationship that is going to connect, electric field intensity with potential. What is that relationship? E is equal to minus del V is the relationship. Am I right? E is equal to minus del V is the relationship. So in the place of E here, I am going to write minus del V. Is it okay? Minus del V. Now what happens? Minus sign, I am taking it outside here. Minus sign is taken out. So minus epsilon, del into del becomes del square. Del square V is equal to rho V. Is it okay? So in the next step, what I am going to do is I am going to take that minus sign to the right side. So minus sign present in the left hand side before epsilon will be going to the right hand side. So what will happen is epsilon del square V will become minus rho V. And if I take this epsilon to the other side, it will become divided by epsilon. So del square V is equal to minus rho V by epsilon is the actual, what is it? Is the actual Poisson's equation. So what happens is the expression becomes del square V is equal to minus rho V. Rho V is nothing but volume charge density divided by epsilon. This is, I am going to call it as Poisson's equation. Is it okay? Very simple derivation. Only thing is you have to remember 2 or 3 basic equations. What are the 3 basic equations you have to remember is you have to start the derivation with the Gauss law in point form, which states that del dot D is equal to rho V. So the derivation has started with this particular equation. I'll tell you. Yeah. See, with this particular equation, we are going to start the derivation. It is del dot D is equal to rho V. So this is the actual Gauss law in point form statement. Then what I am going to do was I am going to use this particular equation. Is it okay? This particular equation, I'm going to put it in the place of D. Then it reduces to some other term. Then in the place of E, I am going to put this particular equation. Okay, so it will become in terms of V. And finally, we can achieve the expression of Poisson's equation like this. That's all. This is how we have to derive Poisson's equation. Okay, very simple. And Laplace equation is again very easy. The point is, for deriving Laplace's equation, we have to consider, right, the volume charge density to be 0. So can anyone tell, if I put volume charge density rho V as 0, how this expression turns into? Can anyone tell? Rael and Celicia from B section, you are available in the class? Rael?
Yes, sir. Good morning, sir.
Yeah, good morning. Have you got my point? I told like how to derive Laplace's equation is we can derive it from Poisson's equation itself. What we have to do is we have to take volume charge density as 0. Now can you tell me, Celicia, what is the expected Laplace's equation expression?
So we have to just equate the particular thing into 0. Del square V is equal to maybe it is 0
minus rho V by epsilon. So rho V will become 0 means
0,
0 by
yeah.
epsilon, it will become 0. So
0.
del square V is equal to 0 is the
Laplace
obtained equation, which is called Laplace's equation. Okay, Celicia?
Okay, sir.
Yeah, thank you so much.
Okay.
So Laplace's equation, we can derive it very easily from this Poisson's equation. Okay, just you take rho V equal to 0 from the Poisson's equation, you can get you can get the Laplace's equation. Okay, that we will see now. I'll move on to the next slide. Yeah, Laplace's equation. By taking rho V as 0 in Poisson's equation, del square V is equal to, this will become del square V equal to 0. Hence, I can say del square V equal to 0 as the Poisson's equation. Okay, this is what is the derivation of Poissons and Laplace's equations. Any doubt in this derivation? Okay, Kritika, thank you. So very important derivation. Okay, so this derivation may come either for a 4-mark question or for a 6-mark question. Derive Poissons and Laplace's equation. So along with this, what you are supposed to write is for different coordinate systems, what will be the Poisson's equation? So we know already how to write del square V for different systems. For example, if I am taking a Cartesian system, how to write del square V, we know. That should be equated to minus rho V by epsilon. If you do that, you can get it. See, this particular thing I have taken it from the book actually. For Cartesian system, del square V, it's nothing but del dot del V. Am I right? So this particular thing I am speaking about. Del dot del V. Okay, it is nothing but we know del V is nothing but gradient, potential gradient, and to that particular potential gradient, if you take the divergence, what will happen is you will get this particular value. Am I right? It becomes dou square V by dou x square plus dou square V by dou y square plus dou square V by dou z square, and that has to be equated to minus del rho V by epsilon. If you do that, you can get the Poisson's equation for Cartesian system. Okay, similarly for cylindrical system, this particular expression. Okay, you can get or see these answers from your mobile app also. Okay, similarly for your this thing, what is it, for your spherical system also, you can get some expression like this. Okay, so you are supposed to write these things also. Okay, that is what is actually expected. So this is our first topic of today. So we have derived the Poissons and Laplace's equations. Okay, now comes the next question. It is next topic, very important topic it is, as far as 2-mark is concerned, as far as problems are concerned, and again as far as derivations are concerned. This particular thing is very important. What is meant by dipole? Okay, simply we call it as dipole, but it stands for electric dipole. Electric dipole. So definition of electric dipole is the first line. An electric dipole, or 1 minute, Pavitra, you want the previous slide. Okay, Pavitra, once completed, you please intimate.
Yes, sir, completed.
Yeah, thank you. So what is dipole or electric dipole means? It is that two equal and opposite charges separated by a very small distance. So di means it is 2. Di means 2, right? So two equal and opposite charges which are separated by a very small distance. We are going to call that particular arrangement as electric dipole. Is it okay? Then comes a question, what is meant by dipole moment, or I can say electric dipole moment. Definition is the product of charge, because we are having two charges which are equal and opposite. Okay, so the product of the charge with their spacing. Spacing means how they are separated. You know, they are separated by a very small distance that we know already. That particular distance, the product of these two things will give you the answer. We call it as dipole moment, or we call it as electric dipole moment. So these two definitions are very important. Electric dipole moment has got a notation called small m. So m will be equal to q into d, where q is the charge and d is the spacing. I am going to consider one arrangement in which I am going to have plus q and minus q be the charges which are separated by a small distance d. Then the product of charge q and spacing d is called dipole moment. Okay, I am going to consider one arrangement. Let us take P as a point at a distance of R1, R2. Okay, let P be any point at a distance of R1, R2, and R from plus Q, minus Q, and midpoint of the dipole respectively. That is, point P where it is placed is from plus q charge at a distance of r1 it is placed. Then at a distance of r2 minus q is placed. Then from the midpoint of this particular charges, again, I'm taking the distance as r actually. From midpoint of the charges or line to the point, the distance is taken as r. So you can see this diagram so that you can understand. Okay, this is what I am actually coming to say. So two equal charges. I am having two charges here. Let us use a pen so that you can understand. I'll go to some other color. 1 minute. Yeah. See here I am having a positive charge plus q. Okay. Then I am having negative charge minus q here. Okay, in a line. Okay, so these two charges are separated by a very small distance d here. Then where this point P is located, that is what is our interest. Where this point P is located is from plus q charge at a distance of r1 it is placed. Then from minus q it is placed as r2 distance. Then from the midpoint the distance is r actually. This is what we have explained now. Okay. Now I will come to the next slide. Have you taken this particular diagram? Very simple diagram. It's just a two-dimensional picture wherein y-axis and z-axis have been shown here. Okay, we call it as a dipole, right? Yeah, I'll go to the next slide now. 1 minute. Yeah, so very simple derivation. So we know already from the basics that the expression of electric field intensity, whenever I am writing the expression of E, in the denominator you will be writing R square. Have you remember that? For line charge we have written rho L dl by 4 pi epsilon R square. Also for this thing, what is that? Uniformly charged circular disk, also we have written E expression dE as rho S ds by 4 pi epsilon d square. Am I right? So difference between this electric potential and electric field intensity is that in the denominator R square will be coming for electric field intensity and just R will come for potential. That is the very basic thing we have seen. Because E is equal to minus del V, we are going to differentiate potential or V expression to get E. Am I right? So what happens automatically is R 1 by R square will become 1 by R, because integration of 1 by R square is 1 by R just. Due to that reason, potential at point P due to plus Q charge. So I am going to take potential expression due to plus Q charge at point P as V1. And I think somebody's mic is turned on. Can you unmute? Okay. So thank you so much. V1 is equal to Q by 4 pi epsilon R1. The distance is R1 here, really. From point P to charge plus Q, the distance is R1. So potential becomes this. And potential at point P due to charge minus Q, it is nothing but V2 I am going to consider. So V2 is equal to minus Q by 4 pi epsilon R2, because the distance between minus Q charge and point P is R2. So I am taking minus Q by 4 pi epsilon R2. Now what happens to the resultant potential? The resultant potential. Okay. So this I think I'll come to the board also so that you can understand. 1 minute, I'll come to the board. With this PPT, I'll share. I'll stop sharing. I'll come to the board now. 1 minute. Is the board visible? Is the board visible, ma? Yes, Renuka Devi, now. Yes, Merlin, thank you. Okay, good. See, actually, we are going to see something on dipole, right? Dipole. What is dipole? We have seen already, and the arrangement what we have taken is like this. Sorry, I'll go to some other marker. Good. So I'm having a line like this, and the axis, right? I'm having point P somewhere here. Okay, so point P somewhere here. So what I am doing is like plus Q charge is placed here, minus Q. So this is plus Q, this is minus Q, this is my origin. This is separated by a distance D. Then only it will become dipole. Okay, right now. Okay, and I am going to join this midpoint also. This midpoint. Okay, so this distance I am taking it as R1. This is R2. This is R. This is what is our arrangement. This is maybe we have taken a two-dimensional axis, so it becomes y-axis, or x-axis, and z-axis, whatever it is. So this is arrangement. I am going to call it as a dipole. Okay. Now what we are going to do is, what we have written is potential at point P due to plus Q. What is the expression is plus Q by 4 pi epsilon and its distance. Okay. In the same way, if I write V2, V2 means potential at point P due to minus Q charge. So minus Q is the charge. It becomes minus Q by 4 pi epsilon. Distance is R. Okay. Next step, what I am going to do is I am going to find the resultant of these two potentials. So V is equal to V1 plus V2. V is equal to V1 plus V2. Okay, if I do that, what will happen? Actually here Q by 4 pi epsilon R1 minus, here plus, here minus, so it becomes minus Q by 4 pi epsilon R2. Right? So how this can be written is, I can take Q by 4 pi epsilon as a common one outside. Remaining is 1 by R1 minus 1 by R2. This is my resultant potential. Okay, very simple derivation again. That's why I am telling it. Okay, now from the figure, okay, here I am writing from the figure and from basic mathematics, right? You assume that this particular point P, is too far away from the dipole. This is the dipole I am telling, right? The distance is too far. You assume like that. Okay. What happens to R1 now? The point P is placed at a far away distance. So what will happen to R is, it becomes R minus d by 2 cos theta. So what is that theta? I'll tell you. See, here I can make arrangement like this 90 degree. Okay, and this particular angle I am going to call it as theta. Okay, so cos theta means this is 90 degree. So obviously this is my hypotenuse. Total distance is R minus d by 2, because this is total d, this is d by 2, this is another d by 2. D by 2 cos theta. That is my adjacent side. So R1 will become this, and R2 will be of the same values, but will be of a larger value. This is a smaller value because of this minus, and here R2 is the lengthy one. You can see it from the diagram itself. R1 is small and R2 is length. So R2 will be same expression, because here also the arrangement is same. This angle is again theta. So it will become R plus d by 2 cos theta. Now what I am going to do here is, I am going to substitute the values of R1 and R2 in this equation. Okay, in the previous answer, I have got one expression for potential, right? Here I am going to substitute these two values. Okay, so what will happen now? So I will erase the diagrams so that we can derive comfortably. I don't want these expressions also. I want only the final expression. So in this final expression, I am going to put these values. So I have taken already q by 4 pi epsilon outside. What is remaining is 1 by r1. So r1 is like this, r minus d by 2 cos theta minus r1 by r2. So r plus d by 2 cos theta. Okay, so now we will erase all the remaining things. I hope you might have copied it. Very easy and very important also. Now we will do our basic mathematical operations. So what we can do it now, we can take LCM here. So a minus b, a plus b like arrangement. So it becomes a square minus b square. Am I right? So it is like this. At the top, what will happen? Cross multiplication. If I take LCM, because I very well know students from school nowadays, they are much lagging in taking what? LCMs. I think this LCM is correct. Anybody has got doubt? So product of these two is here. It is like a minus b, a plus b. So here it will become a square minus b square. Okay, a square minus b square. At the top, term cross multiplication will come here, minus of this term. So minus r plus b. What will happen here is plus r with minus r gets cancelled. These two gets cancelled, right? What is remaining is actually q by 4 pi epsilon. Remaining is 2 times d by 2 cos theta divided by this term r square minus d by 2 square cos pi theta. So these two 2's also can be cancelled. Okay, what is remaining now? Q by 4 pi epsilon d cos theta by r square. Since r square value is much greater when compared with the d by 2 square. We already know for electric dipole, what the thing we know already? D is very small because separated by a very small distance is the condition. So when compared with r square, this term will be negligible. So I have neglected that and I am writing r square above. Now we know that what is actually we call it as what is it? Dipole moment. Actually q into d, the product of these two terms, we are going to call it as dipole moment. So this can be written as m cos theta by 4 pi epsilon r square. This is the expression for electric potential. Is it okay? Here, if you want, you can write the reason. Since m is equal to q, this reason also you can write it, no problem. So here, what I can conclude is this shows that the potential is directly proportional to the dipole moment. Directly proportional to, that is, I can write it even if you want. V is directly proportional to m, and in turn V is inversely proportional to the square of the distance. So by accumulating these two, I can write m by r square. So this is what is the inference I can make from the derivation of electric dipole. Any doubt in this derivation? Anybody has got any doubts? Doubt Raja? Derivation? Okay, thank you so much for your response again. I will now close the camera. I'll come back to the PPT. Yeah, this is the slide which we are seeing it. So resultant potential is written. So R1, R2 we have defined, and finally we are deriving the expression of potential, and we have got m cos theta by 4 pi epsilon r square. This shows that the potential is directly proportional to the dipole moment and inversely proportional to the square of the distance between them, or distance. Okay. Next, we will move on to a very interesting small topic. We call it as equipotential surfaces. Its name itself will suggest some idea. What is equipotential? Potentials, if in a surface, potentials are equal, it becomes a equipotential surface. Or I can say a surface in which potentials are maintained to be equal. Values are equal, it becomes equipotential surfaces. That is what is the definition for this, but they are giving in some other terminologies. We will see to it. If all the points which have equipotential, so we are having 2 or more points, and if all the points are going to have potentials, equal potentials, if all the points are joined together to form a surface, then that surface we call it as equipotential surface. So if all the points which have equipotentials are joined together to form a surface, then that surface is called as equipotential surface. Or the definition will come in this way also. Any surface over which the potential is constant in an electric field is called an equipotential surface. So both the definitions are correct. Any surface over which the potential is constant in an electric field is called an equipotential surfaces. These surfaces are very close to each other, where the electric field is strong and also perpendicular to the surface. Okay, these surfaces will be very closer to each other when or where the electric field intensity is very strong and it is perpendicular to the surface. At those areas, the surfaces will be placed very close to each other. Okay, we are having 2 types of fields for our discussion. One we call it as a uniform field. Another one is to be non-uniform field. Uniform field and non-uniform field. As the name tells, what is uniform field is, a uniform field is a one in which electric field is constant at every point. Okay, we from the primary schools itself, we know the meaning of the term uniform, maintaining the uniformity. Why we are given with the uniform as far as our schools are concerned. Okay, for having a uniform show. Okay, so uniform field means it is a one in which the electric field is constant at every point. Okay, a common way to produce a uniform electric field is with the very simply by taking a parallel plate capacitor, which is going to act as a dielectric. There we can see there is a uniform field, because at every point of the parallel plate capacitor or the dielectric, the electric field flow is going to be a constant one. Okay, the electric potential increases linearly with the distance. So in these parallel plate capacitors, what will happen, you know, electric potential V increases linearly with the distance. Okay, so uniform field is nothing but it is a one in which the electric field is going to be constant, kept constant at every point. Okay, that is what is called uniform field. Now I will come to non-uniform field. It is a one in which the electric field is not constant at every point. There it is constant, here it is not a constant. So in non-uniform field, the field lines tend to diverge in the direction. It tend to either diverge or it may converge sometimes. Okay, a non-uniform field may be produced due to point charges also. Because if I am having a dot charge or a point charge, we don't have any specific shape by which the electric field line should flow. From left to right தான் போணும், right to left தான் போணும், எந்த ஒரு இதுவும் கிடையாது. பாயிண்ட் சார்ஜ்ல பாயிண்ட் சார்ஜ் இருந்து என்ன ஆகும், எங்க வேணா டைவர்ஜ் ஆகும், because it is having a wide environment. So to the environment it may diverge to any direction. So it becomes a non-uniform field. For that only I have got some picture. See, this first left hand side picture is the uniform field, wherein if I got a parallel plate like this from left to right, or from, if I am having a permanent magnet from north pole to south pole, the magnetic flux line should flow. Okay, that is the consistency, right? From left to right it will flow, or from right to left it has to flow like that. So it becomes a uniform field wherein I can see the electric field to maintain its constancy. But as far as the right hand side picture is concerned, wherein a point charge is located, see, it can diverge anywhere to the space. It becomes a non-uniform field wherein electric field will not maintain any constancy, Okay, next very important 2-mark question is define field utilization factor. So field utilization factor is defined as the ratio of, mean electric field to maximum electric field. Eta efficiency போடுவோம் இல்லையா, that eta is the notation used for field utilization factor, which is defined by the ratio of mean electric field to maximal electric field. Okay, next we will touch through the basics of capacitance. What is a capacitance? A capacitor, you might have studied resistor, capacitor, inductor. What are the active elements, what are the passive elements, then why they are called. So what is the basic property of resistor, inductor and capacitor? Everything you might have studied. Okay, A section I taught them in the circuit analysis paper also. Okay, so a capacitor is an electric device which consists of two conductors separated by a dielectric medium. We know that. Okay, so in the bottom diagram also you can see that is a parallel plate capacitor wherein positive charges are there in the left hand side plate and negative charges are there in the right hand side plate. They are separated by a distance d whose permittivity is epsilon, and it is supplied with a battery. It is driven with a battery of voltage V. If this is the case, here there exists a capacitance. That is what we are going to tell. Okay, so very simply, a capacitor is an electric device which consists of two conductors separated by a dielectric medium, and capacitance is the constant actually. Okay, that we will see in the next slide. See, the capacitance of two conducting spheres is defined as, how we can define capacitance normally? C is equal to Q by V. This particular formula is very popular, am I right? See, this particular formula is very, very popular. You might have seen everywhere. C is equal to Q by V, or Q is equal to CV is the very popular formula, and Q is actually the magnitude of charge, and V is the potential difference between the conductors. So ratio of Q and V will give you the capacitance value. We know already the unit of capacitance is farad, F, or from the definition, if you want to write the unit, for charge unit is coulomb, and for potential it is volt. So coulomb per volt is also another unit for capacitance. Okay, also we know that electric flux density, normally current density na enna, current by area இல்லையா, அந்த மாதிரி electric flux density how I can define is electric flux by area. And from the Gauss law we know that electric flux is equal to charge இல்லையா. பாருங்க, normally electric flux density D will be defined as electric flux notation வந்து நம்ம psi ன்னு யூஸ் பண்ணுவோம் இல்லைங்களா, psi divided by area. Okay, this is the actual formula for electric flux density. But we know from Gauss law that என்ன தெரியும், psi is equal to total charge enclosed. இது நமக்கு தெரியும் from the Gauss law. அப்போ D என்ன ஆகும் கேட்டிங்கன்னா, it will become Q by A. அப்படிதான் அங்க Q by A வந்துச்சு சரிங்களா. So D value also we note here. All right. Okay. Also we know this particular formula. What is that? இப்ப பாருங்க, நமக்கு என்னென்ன ஃபார்முலாலாம் தெரியும்னு கேட்டிங்கன்னா, I will write at the top what we have seen in the previous slide. So what we have written is D is equal to Q by A. We have written. In this slide we are going to write D is equal to epsilon E. This formula also we know. So both the left hand sides are equal, am I right? Both are D here, am I right? So what we can equate is right hand sides we can equate. So that is what we have done here. Q by A is equal to epsilon E. So from this, what is Q is? Q is equal to A into epsilon E, that I will get. Also, we know E and V relationship. நமக்கு என்ன தெரியும்? E is equal to this formula we know basically minus del V அப்படிங்கிற ஃபார்முலா தெரியும். E ஓட யூனிட் நான் என்ன சொல்லியிருக்கேன் அப்படின்னா வோல்ட் பெர் மீட்டர்னு சொல்லியிருக்கோம் இல்லைங்களா? வோல்ட் பெர் மீட்டர் அப்படின்னா என்ன அர்த்தம்? பொட்டன்ஷியல் டிஃபரன்ஸ் பை சம் டிஸ்டன்ஸ் ஆர் லென்த் இல்லையா? வெல்கம். ஸோ நம்ம இந்த ஃபார்முலா எழுதிக்கலாம். E is equal to V by D. ஸோ இந்த வேல்யூ ஆஃப் E எடுத்துட்டு போய் நான் என்ன பண்ண போறேன் அப்படின்னா I am going to this value of E, I am going to take it and I am going to put it here. So what will happen now? Q will be equal to A into epsilon V by D. So if I take this V to the other side, so it will become a division. So Q by V equal to epsilon A by D னு கிடைக்கும். Q by V அப்படிங்கிறது என்னங்க? Q by V அப்படிங்கிறது ஒண்ணும் இல்ல, capacitance. So capacitance is equal to epsilon A by D, where epsilon is the permittivity, A is the area of cross section, D is the distance. So in this way we can define the concept of capacitance. So capacitance C is equal to Q by V, or I can say epsilon A by D. Epsilon in turn, how we can write? We know that already. Epsilon can be written as epsilon நம்ம நார்மலா எப்படி எழுதுவோங்க? Normally epsilon will be written as the product of epsilon naught and epsilon r. So இதுல epsilon naught அப்படிங்கிறது வந்து absolute permittivity, epsilon r is the relative permittivity, and this epsilon can be written as epsilon naught into epsilon r. A will come as usual by D. Unit is farad or coulomb per volt. What is the value of epsilon naught? Can anyone tell? What is the value of epsilon naught? Either 8.854 into 10 to the power minus 12 farad per meter, or 1 by 36 pi into 10 to the power plus 9 farad per meter. Both the values are there. So this is what is the basic concept of capacitance. Okay. Okay, next slides and all we will see it tomorrow. Okay, so to summarize what we have seen today, very simple summarization I'll give it. So we have started our discussion with what we have started with Poisson's and Laplace's equation. We have started. We have derived both the equations for electric field. Then what we have done is we have entered into dipole. For an electric dipole or for simple dipole, how to derive the expression of potential, that also we have seen. Then we have entered into what is it? We call it as equipotential surfaces. So what is meant by equipotential surface we have seen. Then we have entered into uniform field and this non-uniform field. Along with that we have seen what's the definition for field utilization factor. Then we have entered into capacitance. Concept of capacitance is concerned, how we are going to do that. The concept of capacitance, that's what we have discussed again, and wherein a dielectric is placed, parallel plate capacitance is placed, and how there a capacitance is getting formed, and how to define capacitance, that also we have seen with a small derivation. So we have got now one expression for capacitance. C is equal to Q by V is one formula, another one is epsilon A by D, because some problem, two more problems may be asked to find a capacitance value just by giving the dielectric plate separation and area of cross section. Just they will give these two values, and medium they will give it. Okay, you may be asked to calculate capacitance, means you can make use of this particular formula epsilon A by D. By that you can calculate the capacitance value. Okay, so this is what our session today. Time is exactly 11:40. Anybody has got any doubts, you can clarify it now. Any doubts? No doubts, sir. Okay. Okay then, thank you so much for your patient listening. Tomorrow we will discuss with the next two topics. So by tomorrow or on Saturday we will try to complete our second module. Only little bit portions are left out. With this, we will close our session. Thank you so much.
Thank you, sir.